very excited to have Joel Odom from GTRI. He is a senior research scientist working with the Cybersecurity Information Protection and Hardware Evaluation Research Lab. And today's talk will be on modern malware and security techniques for better software evaluation. Here's all Odom.
Thanks. Is this on? Audio, visual? Okay. Good. I'll assume so. Good. Good. Thanks, Maria, for the introduction. Thanks for letting me be here to kick off the lecture series for the new season. I'll give you a little bit of background about myself. First, just a minor correction. The title is a little bit misleading. We're going to touch on malware, but there are other groups who are much more familiar with malware than I am. My specialization, and really it's my teams who are the brain of my operation. I just get to get up here and talk and make myself look like I know what I'm talking about. But we specialize in software security. So get your bearings. I work for GTRI. This is Georgia Tech Research Institute. We're a part of Georgia Tech. Most of you are probably familiar with it, but for those who aren't, we're the applied research arm of Georgia Tech. I'm considered a faculty member at Georgia Tech, but I'm not a professor, not on a tenure track. I have taught before. I've taught the Introduction to Information Security course here. We collaborate commonly with our academic colleagues, but we're just a separate side of the house from Georgia Tech. My particular lab, the Cypher Lab, is really the cybersecurity lab of GTRI. We do all things cybersecurity. There's very little that you will find in cybersecurity that is not somewhere in someone's bailiwick within our lab. So we have a group that does malware analysis. Indeed, we have a group, my group does, I'm within a larger group that does the security of embedded systems and cyber physical systems. My particular expertise is software assurance. We also have a group that does secure networking. We have a penetration testing team. We have a group that does multi-level security systems. So there's a lot going on at GTRI. We also teach professional education courses in cybersecurity, and we've touched, just like I said, about everything that has to do with cybersecurity. I want to talk about software assurance today. Now, I have a challenge, and that is that there are a lot of people in this room who are already well versed in software security and will understand a lot of the techniques that I'm going to talk about. But there are also people in the room who have less of a background in computer security. I need to be able to meet the kind of meet in the middle. So here's the assumption I'm going to make. Here's where I'm going to land. I'm going to assume that everyone in the room pretty much has some strong computing background and understands the basics of programming and at least understands the basics of computer architectures. We're going to see some assembly code. I'll talk about that a little bit. There are going to be people I'm going to assume that, but I'm also going to assume that the techniques that I'm going to present here, maybe you haven't had a great chance to delve into. So maybe that's going to be the happy middle so that we can reach as both sides of the audience as far as those who are very technical adept at computer security and those who are more beginning to think about computer security. Maria likes it in these lecture series when we can talk about the kinds of projects that we're doing within our organizations. And I'm going to talk about that a little bit. Unfortunately, because of the nature of our work, there's a lot that I can't talk about in a public lecture. And I always hate it when people say that. And it sounds like it's a cop-out for hiding something. But frankly, the fact of the matter is I have to be a little bit generic in what I say. So if I seem a little bit guarded at times, that's why. It's Friday afternoon. We have pizza. We're supposed to have a little bit of fun with this. So let me set the stage by going back in time to just shortly past World War II to the Tech Model Railroad Club of MIT. At the Tech Model Railroad Club at MIT, there were really, and there still are, two kinds of students. There were the students who enjoyed the modeling that happened above the layout, that is, working with the details of the trains, painting, making the layout just absolutely beautiful and just a nice, realistic model railroad layout. Then there were the students who enjoy working below the layout and on the signals and the power. That is, making the train move and do what it's supposed to do. When you have a big model railroad layout, and you have lots of moving pieces, there's complexity involved in that. In 1946, there's probably a few in the room who can remember back that far. 1946 was the dawn of computing, right? There were not readily available computers to control things like the railroad layouts that we would expect to have and use to control them today. So when the students at the Tech Model Railroad Club came up with a clever way to do something, they called it a hack. So for example, one of the hacks that they had was you could stand at the control station of the railroad layout. You could select the portion of the track that you wanted to control, and their system would disambiguate your control inputs from control inputs that came from other stations to control the layout at the large railroad layout. This was done with mechanical relays, mechanical switches, and equipment largely donated from the phone company. As time went on, as computers started to appear on the MIT campus during the 1950s and into the 1960s, this same group of students took their culture, their hacking ethos, and the terminology forward and brought it into the computer labs of MIT. As the years went on, the term hacking and hacker became popularized. Personal computing started to appear in the 70s for businesses and home. Especially into the 80s, we saw the rise of personal computing. And the term hacker took on more of a negative connotation. It took on a connotation of people who tended to break into computer systems and do malicious things that they're not supposed to do. And we still use it that way today, rightly, though it's interesting to note that recently the term hacker has actually picked up a little bit more of its original meaning when we talk about things like life hacks or hackathons or a hack of the day. This kind of terminology. I'm glad it's taken on this less malicious tone these days. Software assurance is really about avoiding software hacks. So most of the people in this room probably have done some kind of software hacking before. We all enjoy it. We love it. We like to take computers and make them do things that they're not supposed to do, special tricks. There's nothing wrong with that. It's a lot of fun. But we also live in a world where we all carry smartphones, for example. And on our smartphones, we want to be able to access our mobile banking site, and we want to be able to look at pictures of cats. We want to be able to install puzzle apps from possibly dubious sources, maybe from different kinds of app stores, but we also want to be able to do our secure business logins from that, like our two-factor authentication and other applications that require security. So the operating system on a modern mobile device is supposed to give us certain guarantees. That is, the different applications are not supposed to interact with each other unless you explicitly allow them to do so. And the operating system itself is supposed to be closely guarded, right? So this stands in contrast, by the way, to the state of computing in the 80s and even into the 90s to some extent, when there was assumption that with personal computing, if you were running a piece of software, you knew where it was from, you trusted it, and all the software could talk to all the other software. The address space had a flat memory layout. There was not a lot of protection. In modern and mainframe computers and large systems in that era, there were protections. We saw that businesses were realizing the need to have different compartments of security, different user logins, and the ability to share systems. But it wasn't so in the personal computing field. We're still to this day paying that debt, right? So in the 90s with Windows and Apple, and that we saw that business computer systems that ran on personal hardware were deployed. They're supposed to give us access controls, but we still know that OS 10, we know that Windows and even Linux, there are vulnerabilities that exist in those operating systems and in the software that run on those operating systems. This is really what we focus on when we talk about software security, is how can we, one, write software that is secure against these kinds of attacks that we see that spreads malware and spreads viruses. And then two, on the flip side of this, how may we go about exploiting software? So to understand how to secure something, I think it's important to understand how to exploit it. And that's a lot of fun. As a matter of fact, a lot of the middle and technical portion of this talk will talk largely about exploitation, because that's what we need to be able to ensure that we can write secure software. One thing I like to call out is that this doesn't just pertain these days to mobile devices or to desktop computers. It also very much pertains to embedded devices, or even the Internet of Things, which I tend to think of as the extreme end of embedded, where we have Linux on a light bulb. The recent rise of the botnets, the Mirai botnets, and then the Petya and these other botnets, these relied on weaknesses in these Internet of Things devices to spread. It's a new security landscape. These pictures here show what's going on. This is the Delta Electronic In-Flight Entertainment System, and you can see it runs Linux. It runs applications on Linux. So we're entering a world where security and security across the board is more and more difficult to guarantee. So what is software assurance? Once again, I disambiguate software assurance from enterprise assurance overall, our network operations. I think of software assurance as taking and ensuring the security of an individual piece of software or an individual operating system, in contrast to network operations, for example, where we do maybe pen testing of an entire enterprise and organization and try to find the overall weaknesses in its network. Software is complicated, right? Linux kernel, I did this slide months ago. It's what's probably grown another order of magnitude by now, right? The Linux kernel contains over 19 million lines of code, 14,000 different contributors, right? It's easy for just one system to fail. And this, by the way, doesn't even include statistics from the applications that run on the kernel, like Apache or the other applications, some of which may run with root privileges. There's a lot that could go wrong. I love this graph. This is a graph I put together. There's a database that is maintained by an organization called MITRE. MITRE maintains a database of common vulnerabilities and exposures, CVEs. It's just a database of problems in computer security, and it gives the security community a common terminology and a common way to think about particular exploits and particular problems with computer security. I categorized the raw CVE count by year, and the statistics lie a little bit. Some of these CVEs are reserved or may have not been fully developed. But I think that the trend is telling. In 1999, it was down there. You see this linear growth. And it's not stopping, even though in the last 10 to 20 years, I think that computer security has become a lot more in the public eye. Microsoft has gotten much better, much better than they were 20 or even 15 years ago about the security of Windows. Yet the CVE counts still continue to rise. We still continue to see exploits like Eternal Blue pop up that spread malware and make headlines. So I told you I like this graph. The reason I love this graph is because it shows that I will never be out of a job. As long as I can keep my ethics clean, there's always going to be security work to do. And for those of you who are on a computer security track, you should also find this either encouraging or discouraging, just depending on the way you want to look at it. There's a pattern, though, that I want us to recognize that we teach in our cyber systems course. Bugs in software lead to vulnerabilities, which leads to exploits. So a bug could be something like a crash. It could be an unexpected state in the computer program. It could be a logic error that ultimately opens up a vulnerability. Ultimately, in order to understand what kinds of bugs lead to vulnerabilities, we're going to have to just learn by doing and by example. So the best hackers are the ones who just get in, roll up their sleeves, and do the hack of the day, the capture the flag. There's a couple capture the flags going on even this weekend that some of you may be taking a part in. That's because bugs, which lead to vulnerabilities, and that ultimately lead to exploits, that is when you use a vulnerability against the software, this is all about finding exceptions, finding out where things go wrong. So I'm fooling with you here, but while I was actually working on this slide deck, I did indeed see a Microsoft PowerPoint crash. The PowerPoint crashed on me. There was a lot of slides, a lot of megabytes. I was flipping through the slides quickly. What I thought as a security researcher was, aha, I have a crash. Let's see, maybe, and I didn't have the time to do it at the time, right? But I said we could open this up in a debugger, find the cause of the crash, and perhaps it's exploitable. Now, PowerPoint is used to preview files that come over via email. It's used to open files often from unknown sources or downloaded off the internet, even previewing files in a web browser. So it's not impossible that the crash that I saw while I was working on this very slide deck would have been a vulnerability that could lead to some exploitable condition. Without further research, we don't know. So I told you that to understand software vulnerabilities, we need to understand the types of things that can go wrong. Let me just get you thinking in what we call the security mindset. Let's talk about a few types of things that can go wrong. This is by no means an exhaustive list. There's something out there called the National Vulnerability Database, the NVD. It tries to taxonomize vulnerabilities and put them into something understandable. And it's hard to do. It's hard to do right because all these vulnerabilities, again, are weird exceptions. Memory mismanagement is at the top of everyone's list, right? This is kind of exploitation 101, and that's what we're going to talk about more in the next few slides. This is when software does not properly manage its memory. I'll go into that in more detail. These are my I put this list together just kind of based on some of my pet peeves, by the way. The misuse of cryptography or of some security protocols. If you've not taken a cryptography class, you should. What you'll learn in the cryptography class is that cryptography is really, really hard to do right. Computer security in general is hard to do right. There's lots that can go wrong, but especially with cryptography, because when we look at the big actors in the cryptography world, and let's name them, the NSA, the English, the Chinese, the ones who have studied this kind of science in great detail, no one really that we think really breaks the underlying cryptographic primitives. Even the schemes, when they're done right, are very hard to break. We can make schemes that are provably correct. Everyone goes after the implementation. Yet still, it's easy to misuse cryptography, especially for developers who either decide that they can do it better than the libraries that come with the operating system or come with the programming runtime. It's easy to mess up the way that cryptography is done. Protocols, it's easy to mess up the way that protocols are done. TLS, failure to validate server certificates, is often a common source of weaknesses in software and in devices. Misconfiguration happens all the time in software. People leave on default credentials. People configure their web server in ways that are insecure. It's, again, hard to do right. Leaving on debugging features. This is why I put this Easter eggs here. Software developers, I've been in that software development world for 20-some years now, and software developers love to expose debugging features and leave debugging features on because, hey, we may use them someday, or it makes it easier to debug. Well, it also increases your attack surface, right? So Easter eggs is sometimes what we call undocumented features in software. Undocumented features are bad in secure software. They can be fun, but secure software should not only do what it's supposed to do, but it should also not do anything that it's not supposed to do. Otherwise, we open ourselves to vulnerabilities. Race conditions. This is a particular condition where multiple processes or multiple threads, or in the case of the cloud, maybe even multiple systems, are trying to share the same object and they don't get it right. So something happens in the sharing of that object that sets that object into a state where it's exploitable. I want to talk more about memory mismanagement, and to do this we need to dig in a little bit into the way that PC memory works and process memory is managed. So again, process is like an application running on a computer. This diagram is notional, so for those who really understand loaders and architectures of computers, you'll know that the layout here is not exactly what it looks like in process memory, but this gives you an idea that when you start a process, so in Windows it's an executable file, and Linux it's also an executable file, just of a different format, the operating system loads that executable into memory, and it gets it, in modern systems, a virtual address space. So it's not real physical memory, it's virtual memory that the process can then access in order to do things like store process data. But notice also that the program instructions are mixed in typically with the same virtual address space as the data that the process manipulates. We can also have other program data, string tables, kernel data, some data that's some address space that's reserved for the kernel to work in. All of this memory address layout space is intermixed. Now, modern operating systems give us some protection on the way that different parts of this address space can be used, but there are still tricks that we can use to subvert some of those protections. The takeaway, though, the memory, the program instructions, and program data and the data that comes in from the user are all mixed in the program's virtual address space. In particular, Buffer Overflows 101 will concentrate on buffer overflows that happen on the stack. This is a portion of computer memory that's reserved for local variables. It's kind of done in a way where you think of stacking books. As function calls happen, the function will put on the stack the data that it needs locally for that function, so the local parameters and variables for that particular function. If it calls another function, it stacks upon that the next set of variables for the next function that's been called. It also stacks, and this is very important, some control flow data, specifically like the return address, for example. This means that when a function pushes data onto the stack, it mixes the user data that you see up here, the variables, with the return address data. The typical traditional buffer overflow on the stack works like this. If we can write data on the stack that somehow goes beyond the memory allocated for that particular data, we may be able to, when I say we, we're talking about the attacker in this case, the attacker may be able to write data that overwrites program control flow data, thus giving the attacker capabilities, control of the process in question. So in 1988, I was in Mrs. Ogburn's computer science class. This was in middle school, and Mrs. Ogburn posted on the board a newspaper clipping that talked about an attack that had happened on the internet. Now, I had never heard of the internet before in 1988. For me, computers were like my TI-99 at home and the Apple IIs that we had in the computer labs at school. I didn't realize that there were so many computers being connected across the world. But that newspaper clipping talked about a worm that spread between computers across the United States, across the world really, and that had propagated itself. I don't know if it used the term worm at the time, but that's what we call it now. We call it the Morris worm. The Morris worm is a great example of how software security can go wrong. This is code from FingerD. This is the FingerD daemon, which in 1988 typically ran on Unix systems with root privilege. There was very little protection. And what you'll notice from the and it was one of the vectors by which the Morris worm spread. FingerD, for those who haven't used Unix in that capacity before, it allows one Unix system to get information about the users on another Unix system. So it's listing on a network socket, running with root privileges, at least in this time era. And here's the implementation of it. You'll notice a few things. The program, FingerD, allocates the variable line on the stack with a fixed length of 512 bytes. But here, in the gets command, the function reads from standard input into the line. Gets in no way checks the length of data that it's receiving. It reads, it'll populate the buffer, and possibly writes past the end of the allocated buffer. This allows us to do what we talked about on the previous slide. It allows us to overflow the buffer, overwrite possibly control flow data like the return address pointer, and then take control of the program. So in the course of preparing to present this, I decided that I was going to go back in time and I was going to write an exploit for FingerD. I wanted to see how it may have looked. I wanted to give it as a demonstration of how an actual exploit works and how an actual exploit looks. So this is a binary editor. It's just one that shows where I edited and manually created the binary data that I was going to send to FingerD to exploit the system. I want to call out a few things in this exploit. First of all, most of it is just capital A's, right? There's a bunch of 4 ones. Most of it is just unused, just space filler, just that you don't need to to be concerned about. But the important parts are here. At the beginning of the exploit, we see something we call shellcode. Now, shellcode is instructions or data that, when disassembled, corresponds to something, code, that actually executes on the CPU. It's machine language data. So here's the corresponding disassembly of that shellcode. What you'll see here, for those who are familiar with computer architectures, is that this is setting up the stack for a function call, and then it's calling this exec function. Down here, after enough data, after enough padding, we actually have the address of the shellcode, and that's what's going to overwrite the return address pointer on the stack, and that's going to let us exploit the finger daemon. I wrote this, it took me probably a few hours to get it right? It's a little bit of back and forth, a little bit of trial and error when you're writing this. So we'll talk about performing the exploit. This disassembly is the disassembly from the finger daemon. Now, I compiled it on Linux, not on the systems it was originally written on. And I turned off a few things in the compiler, some optimizations. I made my job a little bit easier by changing the way that the compiler and the operating system interpret programs, things that are supposed to prevent the attacker from being able to write an exploit in just a few hours. Doesn't mean the attacker can't write an exploit. It just means that there are some advanced techniques that are involved. So here's the corresponding disassembly. Here's the return address. This instruction sets the program's instruction pointer based on the return address that is on the stack, so that it can clean up that part of the stack and go back to the function that called it. But my exploit has overwritten the proper values from the stack. So you can see here I've run the exploit, and if you do everything carefully enough, you could run the exploit with anyone ever being any the wiser. Notice, first of all, that I ran the exploit in GDB. That was because that's where I developed the exploit. It would have taken a little extra work to actually have written it so that it would be stable in a production environment. But the call out is that the finger daemon, it exited normally. I could have called this in the blink of an eye. So over the network, the traffic would have come in, it would have performed the exploit, the process would have exited normally. Yet what my particular exploit did was it installed a backdoor on the system. It allowed me then to log into the system using a passwordless account that I created. That's buffer overflows 101. That's going back to 1988. It's still largely done that way. I talked about some of the protections that are done in modern operating systems. Let me go a little bit deeper than the first time when I presented this, because I do know that we have a lot of people in the audience who are technically savvy. How do we prevent an attacker from doing this kind of thing? Well, modernly we have what's called ASLR, address space layout randomization. This is one thing that makes it so that the computer, when the loader loads a program into memory, it doesn't necessarily put all of the code at the same spot the same times it loads. It randomizes the layout to some extent so that way it's harder for an attacker to figure out where the code that he may need to use to exploit is. Another thing we do, notice that my shellcode was on the stack. I just pushed it straight through with the exploit. Modern stacks have a bit set in the memory pages called a no execute bit. This prevents the shellcode from running on the stack. It means the attacker has to find another place to put the code before the CPU will run it, or has to find another technique like return-oriented programming to exploit the stack. And then also the last thing that we do, sometimes we'll change this. We'll put something called a canary on the stack, for example. A stack canary is a particular number that if it gets overwritten, you know that the stack has been corrupted, and then the debugger or the operating system can detect stack corruption and shut down the program before something bad can happen. So a few years ago, the College of Computing in 2014 needed a sucker to teach the introduction to the undergraduate information security class. So naturally they called me. Naturally I accepted. I was in the unit where I was talking about TLS, transport layer security. This is the protocol, right, that pretty much secures the internet in a sense. At the end of my TLS unit, I venerated OpenSSL. I said, use OpenSSL if you're going to use TLS. I said it's been well inspected by the security community. It uses good programming techniques. I think it's the way to go and the secure way to go. And then not 2 weeks later did Heartbleed hit. Heartbleed was the biggest, probably the most impactful or potentially impactful vulnerability that we've ever seen in modern times, right? Bruce Schneier, the security researcher, said on the scale of 1 to 10, Heartbleed merits an 11. A lot of security researchers were, no joke, saying don't use the internet for anything that you care about, no banking, nothing but cat pictures until such time as the dust settled, Heartbleed is patched. And then once you do start using the internet again, change all of your passwords, just assume that everything was compromised. So this XKCD cartoon did a good job at explaining the Heartbleed bug. I know that it's too small for you to read, so let me just explain it to you. Heartbleed works like this. The client connects, your web browser typically, connects to a server. During the course of that connection, the TLS session, your client can send to the server something called a heartbeat request, hence the name Heartbleed. The client says, hey server, just want to check if you're still there. If you are, send me back 3 bytes and put the contents in those 3 bytes, put the word foo. Or you can say, send me back 5 bytes and put the contact, tech1, just whichever. And so the server should reply to your Heartbeat request and let you know that the server's still there, and you can check to see that the integrity of the connection still looks good from your standpoint. Heartbleed worked like this. You could send to the server a heartbeat request. You may say, hey server, are you still there? If so, respond with the word foo. And by the way, foo is 65,000 bytes long. And the server would then send back a buffer of 65,000 bytes that started with the word foo, but then after that could be any data that the server happened to be processing on the heap at the time. And the way that Heartbleed worked, we can understand it pretty easily, is that it was simply a failure to mediate and correctly check the data that the user was sending. So we can see here's the OpenSSL code before Heartbleed was patched. The length of the payload of the Heartbeat request, that is the data that's supposed to send back, is stored in this variable payload. That's the length of the payload. OpenSSL then allocates a buffer using payload plus some necessary padding for the Heartbeat response. It allocates it beautifully, just as much data as it needs. There's no problem with the allocation here. Everything is well coded and coded correctly. And then it copies from the buffer where the user's original data was stored. It copies payload bytes of data into the response buffer, then sends that response back to the client. It's obvious when you think about it, though, that if payload is larger than response, it's going to send 65,000 bytes of data off the heap. And here's the neat thing about it. Heartbleed, not only can you do it once, you can do it over and over and over and over again with the same TLS connection with very, very, very little chance of crashing the server. It's possible that you could try that this memcopy could read into a page of memory that would give you a segmentation fault, but it's very unlikely. Whatever the server happened to be thinking about on the heap, maybe from different threads of the server servicing different users, it could be private keys, it could be passwords, it could be anything, would be sent back, and you could do it 64K at a time. This, in a code review, and when you, for those who are students, when you start doing development, you're going to start reviewing one another's code, right? And you're going to start looking over it for problems. This is very unlikely to be caught in a code review, right? Unless you just happen to notice that, hey, this payload has been tainted and is no longer specified by the user. One more example of a vulnerability that I want to talk about. Ken Biddick, who some of you may know, is one of the researchers on my team. He crafted this vulnerability, and it's really clever. It's very, very subtle. Again, it's another vulnerability that is very unlikely to be caught in a code review. And because we have so many technical people in the room, I want to spend a minute. Can everyone see it okay? Is it too faint to read the code? Okay. I want to spend a minute, and I want to see who in the room may be able to see the vulnerability. And while the world comes crashing down, I'll give you some hints. First of all, we're going to read some data. We're going to process it, and we're going to read it into num bytes. And here, we ensure that we won't overflow the buffer. Looks good. If I were doing this in a code review, I would look over this and I would say, yeah, everything is being checked just right. We're even checking to make sure that the fopen worked correctly. We're checking to make sure that we're not going to overwrite the buffer. This is well-written code. But where's the problem? Does anyone see it yet? But that's okay because bytes, this buffer that we're reading into is an buffer of unsigned chars.
Right. Oh, I see what you're saying. Okay.
Look at the declaration of num bytes. Here's an exploit I wrote. This is just a denial of service. I didn't get clever. I just wrote this exploit so that it would crash the program. Why does this crash the program? We're in little endian format on this architecture where I did it. So the first 4 bytes in this case is going to be read into num bytes. In little endian, when you have a signed integer, what does this give you? It starts with an 8. It gives you a negative number. So in this case, num bytes is going to be interpreted as a negative number. It's certainly not going to be greater than max bytes. So this check here on the buffer side will pass. And the program will go right on reading data that the user specifies into the buffer. But here, where num bytes will be implicitly cast to a signed type, and it's just going to keep on reading, overwriting the buffer, writing as much as you care to write into the buffer. This code is absolutely, completely broken. You see how hard it is to catch these kinds of software vulnerabilities. That's why that common CVE database keeps growing. So I want to transition at about this point to the portion of the talk where I start to talk about what is it that we can do about it. I want to talk a little bit about the projects that I have going on, what we've done about it. And I calculate I have, 10 minutes left? Okay. Oh, by the way, here's where I ran it. Like I said, I just got a seg fault. I could have exploited it, but I just only had so much time in the day, right? Notice I compiled it with wall. All warnings turned on, and still the compiler didn't report any warnings, didn't give me any trouble. Code review wouldn't have caught it. It's completely broken. But there is a technique that likely would have caught it. It's called fuzz testing, and that's the first technique I want to talk about. This is something that my team has developed a name for. We've developed a name for ourselves in fuzz testing. Fuzz testing is well understood. It's been happening for 2 or 3 decades. In the last 10 years or so, we're seeing more and more intelligent approaches to fuzzing. My team's expertise, by the way, just to give you a preview of coming attractions, we've made a name for ourselves, fuzzing embedded systems, which is a little bit more difficult. But fuzz testing is this. We take a program that we want to analyze, or an operating system, or sometimes it could even be a protocol, but let's just think of it in terms of a program. Let's think of that particular program we looked at just a minute ago where it reads from the user data from a file. And we start with a set of seed inputs. These seed inputs could be inputs to the program that we know are supposed to work with the program. It could be seeds that have crashed the program in the past and we want to do some regression testing, or it could be seeds that we suspect may be problematic. We just have to generate a set of seed inputs. The idea behind fuzz testing is then to run the program repeatedly with mutating those seed inputs according to a set of rules that are well understood We flip bits, we change bytes, we continue mutating until we find a seed input that causes the program to do something different. Now, I've got a technical audience here, so I can tell you a little bit about what we mean do something different. That is, follow a different execution path. Could be something that causes the program to crash. We really want to search and explore all of the paths that could happen in the program. So notice then, to do this while it's being fuzz tested, we have to somehow be able to examine the state of the program. And we do this, typically, we can either instrument if we have the source code, we could instrument the source code, but sometimes it's easier to instrument the binary, that is to put instructions in the binary that allow us to hook to it almost like a debugger, or we can hook to it like a debugger, or in the case of embedded systems, we might, while we're running emulation, sometimes the hypervisor will let you inspect the process state or the operating system state and know what's going on, right? It's a little more technical than I gave before when I've given this lecture in the past. So we have to understand what's going on with the program. That can be the tricky part. We continue, once we find an input that does something different, we've explored a new path of the program. This is good. So we can continue to explore. We add that really to the pool of seed inputs, and we continue to explore and mutate that input, looking to dig further into deeper paths. If we find an input that causes a crash, then that's good. We like that, because that means that here's something we can report and remediate. And we'll also add that to the set of seed inputs, and we'll start mutating that inputs. We've taken this address space, this input space, which could be infinitely large depending on the program, and we've figured out a way now to search that input space so that it's meaningful, so that we can explore the program and look for inputs that cause unwanted program behaviors that, again, bugs lead to vulnerabilities that lead to exploits. That's the basic idea behind fuzz testing. I'll give you an example. I wrote this vulnerable program. It's pathological in some sense. It has unmediated user input. It has a stack buffer overflow. The code review hopefully would catch this, right? I mean, it's pretty obvious what's going on. Has an unhandled floating point exception. Those usually are not exploitable, but it could crash the program, which could be bad enough, or you could be able to use the unwanted state of maybe crash a thread and then exploit a race condition. It could be part of a chain of attacks. We have a user-controlled format string. So surely enough, I ran Warthog, our fuzz tester, on it, and it found this long input, crashed the program. It found that %n crashed the program. For those of you who speak C, you'll remember that %n writes to the place of memory a point in memory how many characters have been printed so far, right? So this format string allows the user to control process memory to some extent. And then it found this floating point exception. It didn't find Warthog C. It started with Warthog CBC. It just somehow got there sooner, right? So here's the crashes that we found. Would fuzz testing have caught the subtle vulnerability? Absolutely. That's a great case for fuzz testing a program, because certainly it would have flipped that bit, found that a negative number crashed the program. That would have happened soon. The first one, the finger D, certainly would have caught that. That's just a simple read from standard I/O. If you're sending it data, the fuzzer would have quickly found that, hey, there's an input, long inputs in general crash the program. Heartbleed is a little bit different. Heartbleed may not, it depends on how you instrumented the program, and if you had done protocol fuzzing on Heartbleed, you likely would have caught it that way. But just with the kind of fuzzing that I've talked about, it's a little less likely you would have found it. But we can get smarter than just regular fuzz testing. I've talked about how we're searching the input space of the program for inputs. Well, we know, for those who have had theory, we know that the number of paths that a program can follow this is not necessarily a tractable problem. If you want to think of the pathological case, think of a program to get to a certain input path, there's a hash function, and the input data has to match a certain hash in order to get to that program hash, to get to that path of the program. This could be done, malware sometimes does this kind of thing to search and make sure that it's running on an environment that it's interested in running on. So that, obviously, a hash function, if it's done right, we don't know what pre-images will get us to a certain point in the program, so that's not tractable. But sometimes we can do analysis of a program and get smarter than just blind fuzzing. So you look here, I've done this strange set of input where I've chained together a password. We can take a program and do what we call symbolic analysis of the program. That is where we take the binary, we lift the binary into an intermediate representation that we can then solve using mathematical techniques like just the simple set of predicates that you see here. And we can solve for which inputs are going to lead us down a certain program path. What the community, the program analysis community, has found is that user code reviews often find on the order of, there was a study done, so forgive these numbers, I'm not getting them exactly correct, but it's on the order of a challenge binaries where there are hundreds of vulnerabilities. They'll typically find, code reviews will typically find 5 to 10% of the vulnerabilities. They're hard to find. Random fuzzing, symbolic execution will find a much greater percentage of the vulnerabilities. Fuzzing, not random fuzzing, but intelligent fuzzing with inspection of the program state, can get and find even more vulnerabilities. The best thing, though, that we've got so far for finding vulnerabilities in a program are techniques that are typically concolic execution. We combine some dynamic fuzzing with symbolic execution, that is when we have a hard-to-solve code path. We stop, we analyze that particular code path, and we find how we can break through that code path and then send that to the fuzzer so that the fuzzer can continue on its way. In some of the Cyber Grand Challenge binaries, this concolic approach found as many as half of the vulnerabilities, right? The other half, still not there, still very hard to find. So I always talk a little bit about what we do at GTRI. This fuzzing technique that we've done, that I have expertise in, enterprise fuzzing is pretty well understood. Some of you have probably used AFL before. Microsoft has a fuzzing platform. Google has fuzzers out there. It's a well understood technique. So Windows, Linux, even iOS we've done. These, Windows and Linux are again, fuzzed commonly. My technique in particular has done VxWorks and embedded. So you're wondering why there's a picture of a cat up there. If I had been giving this presentation to a sponsor of GTRI, I'd put up an image of the particular kinds of systems that we've fuzzed. Again, it's one of those cop-outs. I can't tell you what we've fuzzed exactly. So I hope you can enjoy this picture of my daughter's cat in lieu of the image. But use your imagination. Think about things that drive critical systems, especially that the government may be interested in. That's what they want us to find vulnerabilities in. That's where the GTRI's expertise in particular lies. So I'm right on, just about on time. Let me end, not going through this entire top 10 list, which, by the way, I just scraped it right off of Carnegie Mellon's Software Engineering Institute website. I want to call it a few things that are important if you're going to write secure software. And that is this. Use effective QA techniques. Don't just check your software. A student, we love you students, but student software is software that is made to do what it's supposed to do, then you're done, right? You submit it, you get the grade. Pound on your software. Use fuzzing. Get past just the regular. Validate assumptions. Test for failure conditions. Expect failures to happen. Minimize the attack surface. Don't be clever. Keep it minimal. Separate your modules into testable functionality. And lastly, this is the biggest one, the number one. Don't trust anyone. Internally in your program, examine your program state, especially when you receive data from outside. Validate that data. Make sure that the tainted data is sanitized completely. Whoa. When I did this originally, it wasn't quite that loud. So I think that we're at the end of the hour. This is good because I don't have to answer any hard questions, but I'd be glad to stick around and say hello. Is that okay?
Yes, so before thanking our speaker, this is a good moment to take any questions from the audience, or otherwise, I'm sure Joel will stay around for a few minutes to chat with your industry if you have any further questions.
I know that you have other classes, so if you got to go, please go. I won't be offended. But are there any questions? Hi.
So I have a question about your fuzzing tool.
Yeah.
Yeah. So the one of the merit of the fuzzing tool is the code coverage.
Right.
How do you measure the code coverage on the Windows platform,
So,
especially for the network redirecting or I/O?
all right. So let me change your question a little bit. So his question was about code coverage. We're not so much interested in code coverage. Hey, Evan. as we are path coverage. So we can, even if we were able to test 100% of the codes, we're really more interested in how do we get to the paths that we get. So in Linux, my understanding is we do it through binary instrumentation. If we get a piece of malware that comes into our analysis platform and we want to do some analysis on the malware, we'll inject commands into there. I think they're similar to debuggers, like int3, just an interrupt or something like that, that will allow us then to inspect that coverage, inspect the state. We can break it. We can look at the path that the code has taken, and we can find out if we've hit that path before. Does that answer your question?
Well, I mean, for the code coverage, like you're basically getting all the basic blocks from the function so that you can go cover all the code things. Like I just want to know, like, how do you guys measure like all the basic blocks, like for the code coverage things?
Yeah, we do basic blocks. So it's basic block coverage, or path analysis using basic blocks. And like I said, my understanding is that we instrument the program with binary instructions so that when a new basic block is found, we can get information back to our analysis tool that tells us we've hit a new path. Okay.
Any other questions? Let's thank our speakers.
Thanks for coming out.